Okay, thank you very much. I mean, it's my great pleasure to speak in this conference, and I want to thank the organizers for the invitation. So to start my talk, I will follow the style of the second talk this morning. So I will start with some examples. So let's think about P2. But now, if we want to study some modular space, if let's say P2 is one object, then we want to look at what possible degeneration of P2. And we all know that P2 can degenerate to P114. In a sense, you say in the morning that you may have a trivial family over a puncture disk. So over the puncture disk, every fiber is isomorphic to P2. But then over the special fiber, you got the P114. And this actually can keep going to PABC for some special ABC. And there are infinite choice of ABC. So if you think about this, what this means in moduli, that means if I want to have a moduli in P2, which P2 is a member of this, then I'd better not have one of these objects. Otherwise, somehow, this degeneration really makes the modular problem not so good in the sense we heard this morning. So then, I mean, there's still some like dipole surface, but with Cauchy singularity. So you might think, okay, maybe the singularity is too bad. But another example is P1 cross P1, degenerate to the, let's say, the cone over conix. So this only have a one A1 singularity. So it's not so singular anymore. But still, we see this kind of phenomena that over a puncture disk, every fiber is P1 cross P1. But over the special fiber is cone over cone, is something different. Then if you want me to really write down a smooth example, I could. But that requires higher dimension. So I'm not going to give you an example explicitly, but I just tell you that there are families of Fano varieties, Fano manifolds, which such as over the puncture disk, every fiber is isomorphic. But on the special fiber, you got something different. So I think historically, this might be the main reason that people don't try to search for a good theory of moduli of Fano varieties, because this kind of thing does happen. But today I want to tell you, indeed, at least conjecturally, there is a good modular theory for Fano variety. But you have to post some extra condition, which is the so-called K-stable condition. And basically, in the spirit of this morning's talk, I mean, you are encouraged to interpret what K means. But so let me just write the conjecture here. So this is a conjecture for some like a certain good modular space of Fano varieties. So let me say the conjecture has three parts. So let me say I fix dimension n and the volume v. So these are two numerical invariants which I fixed. And now I just look at all n-dimensional Fano variety. Here I will call it Q Fano variety. This means X has KLT singularity plus minus KX is ample. So if you haven't heard this terminology KLT, I mean that stands for Karl-Martin terminal. I'm not going to define today, but you probably will see this more, I mean, in Janos's talk. But you just think about that I allow certain singularities. And this kind of singularity is the singularity which we work with when we do minimal program. So this is kind of a natural class of singularities which appear first from the minimal program. So then actually I want to post the condition here, which I call K-semistable. I will define this, what K-semistable means later. Actually, I will give you two definitions. But now I just put it here. That then let's say I want to look at all dimension n, volume V, K-semistable Fano varieties. The first part, say, it forms a forms an Artin stack of finite type. So somehow we only live in the second level in the evolution. So this is the Artin stack. So what I really need here to have a functor to be Artin stack, basically, you can imagine I just need two conditions. I need, first, it's bounded. I need it bounded, so let me put one here. And second is we basically need, it's kind of like a directly open. Or sometimes, I mean, local closeness is enough, but let me really just put it directly open here. So then this is the first part. The second part is, now let me just give a name of this Artin stack, which I call MNV, KSS. SS stands for K-semistable. Then the second part of the conjecture say, this M actually admits a good modular space, which I denote by MNVKPS. So this good modular space, I mean, that's in a sense, I think, first defined by Harold Blum. So somehow, basically, there is a morphism from this stack to this modular space, such that locally it looks like the GIT quotient, although this is certainly not given by any GIT question as far as we know. But we just hope that at least there is a morphism from this stack to some space, which this morphism looks like a GIT morphism. Then, so this I put three here. Then I want to say that this space is projective. So projective, of course, we know it has. We know it's separated. We know it's proper, and then we really know we want to know it's projective. So think about this. What this means? That means, like, for instance, if my P2 is K-polystable, which it is, then it's not allowed to have a P114 in this modular space. So that just means P114 is not K-semistable. And similarly, since P1 cross P1 is K-polystable, then the cone over a conic curve will not be K-semistable. So this is kind of like separating this mean. And what proper means, this is the even stronger condition. Let's just say if I have a family of Fano varieties, which the generic fiber is K-polystable, then I really can fill in this puncture disk with a unique K-polystable limit. So then the question is how to find this limit. I mean, that's quite mysterious. And then at the end, you want to still prove the modular space is projective. So that's kind of the content of this K-modular conjecture. So now I want to give you the definitions of the terminology here, what I mean by polystable and, what I mean by K-semistable. Maybe I should say one more word. So like a GIT case, the point on this good quotient space basically just parameterize K-polystable Fano. So then I'm going to define what I mean by semi-stable and polystable. So again, as I said, this seems to be a quite striking conjecture. I mean, at least when I first think about it in this way, because somehow, given the two examples at the beginning, especially the second one, I mean, the cone over conic, I mean, it has a little bit of singularity, but it's not really that bad. but somehow then we have to find some global conditions to somehow to wipe out this conic curve and only look at the P1 cos P1. And so, as I said, the local condition seems to be not strong enough. So we have to have a global condition. And this global condition is this K-stability. And the main reason behind that we believe this condition could be true is that basically this K-polystability characterizes whether this Fano has the so-called Cayley-Einstein metric. And then we hope that all the Fano varieties with Cayley-Einstein metric form a very modular space. So this is certainly an analytical theory. But then we hope that at the end of the day, we can just give a completed algebraic geometry treatment of this. Well, you will hear this more in the talk. But let's say, so this was the original definition first introduced by Tian, and then Donaldson, who gave a completed algebraic definition. So basically, I look at this X. So my X is a Fano variety. And then I look at this minus RKX. So here, R, I just choose it as sufficiently divisible. So, I mean, but you really think about this R could be larger and larger. So it could be any sufficiently divisible one. And then this I assume this R sufficiently divisible such that this gives an embedding of X into this Pn given by this linear system. And then, of course, since PG Ln plus 1 acts on this, then I can think about that this as a Hilbert point. I fix coordinates, then I think about this as a Hilbert point. Then I pick up a C star, one parameter subgroup inside here. And then I use that one parameter subgroup to act on this Hilbert point. So now I have this C star acts on this point X. And let me just take the limit to be X0. So this is in the Hilbert scheme. So in other words, if I take the family, what I have is I just have a family of X over C, such that outside the orange, then it's just a trivial family, because that's just the family I got by using C star to push forward this Hilbert point. And then I have a polarization, which just give my RKX here, inside here. So basically, I have this kind of picture. So I mean, if you know GIT, of course, this is just say I pick up a one parameter subgroup inside this linear group and look at its limit. And now I want to define some invariance out of this. So first, let me say I just look at the Hilbert function of, maybe I just put it in this way. So now this L0 is just a restriction of this on a special fiber. So it's an ample line bundle. So when K goes to infinity, you can just think about this as A0 K power to m plus A1 K power to m plus the lower order term, because of the psi variation, all the other HI variation. So this is just something like a simple version of psi variation. And then if you apply the equivalent version, so because now the C star acts on H0, X0, L to K. So now I have a C star acts on vector space. So then we know we can find the eigenspace. So now for each eigenspace, I have the weight. So now I take the total weight. So now I take the total weight. So that will be of the form B0 Kn plus 1 plus B1 K power to n plus O K minus 1. So it has degree 1 larger than the dimension. So now I define for this, I define the generalized Fataki invariant. So I mean, in some literature, it's also called the Donaldson Fataki invariant, that I just define this to be B0A1 minus A0B1 divided by A0 square. So this looks like an obscure number, but the definition of K-semistability, which was introduced by Donaldson in this form, is that the X is K-semistable if this is non-negative for all possible R and C star inside GL, PGL, and plus 1. So this is really the main point of this definition. So you usually when you do GIT problem, you embed your X into some fixed Pn, and then to study the group action on the Hilbert space there. But here, when I look at this, I allow the R to become larger and larger, and then I look at all the C star. So if you fix one R, then this is similar to a GIT problem, although it's still not a GIT problem. But at least it's similar. But now the real point of this definition is I allow my R to become larger and larger. So basically, if you think about this definition, you can imagine to check X is K-semistable is a very hard condition, because somehow I have to just use this definition. I have to look at all possible embedding, and I have to look at all possible C star in each embedding, and I have to calculate this number. And it is actually a very hard condition to check. So for instance, you can take an exercise to prove that say P2 is K-semistable. And I swear to you, that's actually very hard. But the one theorem which I proved a while ago, together with Chili, is that indeed it suffice to look at the total family X, which is Q-Grosnin, so normal Q-Grosnin, such that X0 is a KLT Fano. So originally, you have to study all the possible degenerations. Like I have this X. I mean, for instance, if you have a P2, put it in a conic, then you just degenerate to two lines. But here, the theorem say we don't need to look at those. We don't need to look at those degenerations. We only need to look at the degeneration such that the special fiber is also a KLT Fano. So particularly, it's normal. So this kind of restriction on degeneration was built into Tian's original definition. But basically, Chili and we just proved that these two versions provided by Tian and Donaldson are essentially just equivalent. So as I said, because P1 only have one degeneration of P1, then this way we prove P1 is K-semistable. But again, if you think about that example for P2, you find it's not so easy even to use this to prove P2 is K-semistable, because you still have to check all those like a P2 degeneration to PABC, then to calculate the Fataki invariant there. So now I want to give you some like a new definition, but essentially equivalent. So this kind of like a new perspective were introduced in the last like 4 or 5 years, and it may make our understanding of K-stability question of Fano variety improve a lot. So basically, as far as I know, it was the first book song Hisamoto and Johnson, they basically, instead of using degeneration, they basically just look at valuation over X. So originally, this you have this n-dimensional X. You turn it into an equivalent n+1 dimensional object, and you calculate some numbers here. But then Buxton, Hisamoto, and Johnson say, instead of looking at the n+1 dimensional, we just look at the valuations over X. So that's still a n-dimensional question. And then Fujita, Kento Fujita, he defined this beta invariant. So basically, if I have a divisor which is over X, so when I write this, I just mean this is the divisorial valuation over X. So it's not a necessary divisor on X, but it's on a birational model of X. Then we define beta D to be the AXD times minus k power to n minus the integral from 0 to infinity, the volume of minus kx minus t dt. So this function is the so-called log discrepancy function. So basically, say KLT just means this function is always positive. So then this is just the intersection number. So that's just a volume. So we have this positive number. And here we have a volume function. I mean, I wrote it as from the integral from 0 to infinity, but it's actually a finite integral. Here the integrand is from 0 to the pseudo-effective threshold. And then inside that pseudo-effective threshold, this is kind of a continuous function. And then you take the integral. So this is the positive function, and this is the positive function, and then we take the difference. And it's a theorem by Fujita, also independent by Lee, that the X Fano is K-semistable if and only if all the beta D is non-negative. So for all D. So as I said, this essentially just turns this n+1 equivalent birational geometry problem into an n-dimensional problem, because now the number we look at is really just defined over X itself. And let me just give a very quick sketch of one side of this. So basically, let's say let me assume the right-hand side. So we want to prove this direction. So now, as the theorem I mentioned there, this implies that we only look at X such that the X0 is KLT. And then we know, if we look at this divisor, X0, we think about it as a valuation. And then this, of course, is the valuation on Kx. But since X is birational to the capital X cross A1, so this is just Kx cross A1. And of course, Kx is the field inside here. So then I can just restrict this valuation on this one. And then you just apply Bianca inequality, you realize as long as this X is not trivial, this restriction, so if I have a odd X0 restrict on this Kx, it's a form that is a positive number times some divisorial valuation. So here, then we have a divisorial valuation here. Then it's a straightforward calculation that the Futaki invariant of this X is indeed just C times the, let's say, another constant, maybe C prime. So where C prime is positive, which essentially only depends on X and the dimension, but not the curly X. So in other words, just out of this inequality, you say beta D is non-negative if and only if all the Fano invariant is non-negative. So particularly this implies that the X is K-semistable. So this is the one direction. I'm not going to give another direction because you have to then to show that if I assume all this kind of X is Fano invariant is non-negative, the beta is non-negative. That requires a little bit more argument. But you see the spirit of this kind of theorem. So any question? Sorry? No. This D is not necessarily on X. It's exceptional. It could be exceptional over X. That's why I kind of wrote this as funny notation like D over X. So now I can define, maybe give a second definition. Maybe let me read this one. So basically, this kind of new definition, the equivalence with the original one, was mainly improved by Fujita and Chili, but with some other people's contribution. So first, let me just still assume X is always my assumption X is a Q Fano, so it's a KLT Fano variety. Then, as I said, we now define X is K semi-stable if and only if beta D non-negative. So basically, we use that theorem as our definition. And now X is K-stable if and only if beta D is always positive for any D. Here, actually, there is a slight improvement of the argument by Blum and myself. So this is the definition for the K-stability. And we also say X is K uniform stable. Maybe uniformly K-stable. If and only if beta V positive for any valuation V. This again has some contribution from Blum and Jonsson. So here, again, I mean, if I have a valuation, here I only define beta for divisor and but you can replace this divisor by valuation. You can still define the log discrepancy here, and then you can still define the volume function here without much trouble. So then, now I look at all the valuations here. I want to say it's positive. That's kind of uniform stable. And conjecturally, these two should be equivalent to each other, but that seems to be a very hard conjecture. And finally, I want to say X is K-polystable if X is K-semistable. And by the way, if I have this kind of picture, I have a kind of C star family of X degenerate to X0. Then I often say X specialized to X0. So specialized just means specialized under this kind of C star action. So then under this X is semistable, and if X specialized to K semistable X0, then X should be isomorphic to X0. So basically, the polystable just say, in some sense, in this S equivalence, this X should be the minimal object. So if it is specialized to some other object, then actually that should be the self. So basically, you can just think about K polystability as a semi-stability plus the minimality in the S equivalence. Okay, now we can come back to this K-moduli conjecture. I mean, again, I mentioned this before, but when you think about this, it's still kind of surprising. I mean, why do we believe this is true? I think there is one main piece of evidence is that when we consider all smoothable Fano X. So now if we just think about X, but we know that X can be deformed to some smooth Fano X. Now then we add this stability condition. We know the conjecture is true. Maybe except the projectivity. This is by Chili, Xiaowei Wang, and myself. So basically now if I'm not looking at all this smooth, all this like singular Fano varieties. I just look at those who can deform to the smooth guys. Then this conjecture is true. We really have this, at least the proper modular space. We have Artin stack, whose good modular space is proper modular space. So this seems to be quite a satisfying answer. But unfortunately, this proof heavily relies on analytical geometry. So the proof heavily relies on the so-called Yao, Tian, Donaldson conjecture, which is solved in the smooth case by Chen, Donaldson, Sun, and Tian. So what's this Yao-Chen-Donaldson conjecture say? Basically, this conjecture just say, so let's just say, I can just write here that the K-polystable is equal to KE metric. So basically, that's why the complex geometry initially were interested in this K-stability notion, because that's their algebraic condition to characterize this existence of Cayley-Einstein metric. And this, in the case that it's a manifold, it was already solved. So our work using their theorem, and also we use their proof to construct this modular space. So somehow this has there's two disadvantages. First, it uses a lot of analytical stuff, so which we really want to replace by algebraic geometry argument. And the second, because we use analytical stuff, we have to assume this smoothable condition, which we definitely hope we can drop at some point. So, but today all the stuff which I want to talk about is purely algebraic. So I want to discuss some recent work on how to solve some of the steps of the K-modular conjecture completely using algebraic geometry, especially using this like a new definition. But before that, let me mention that so I have like a 6 point here. The first is one, the boundiness was completely no. So the boundiness, this is no. This is a work by Zhang, who is here, but he heavily used the solution of the BAB conjecture by Berka. So somehow use this like a deep theorem in the boundaries of Fano varieties, we can conclude that all the K-semistable Fano varieties with fixed volume and dimension that form a boundary family. So the boundary part is no. And today I want to concentrate on point 4, which is the separateness part. So that's the main theorem today. Is that this is the joint work with Blum, that, so basically our setting is we consider two family over a curve, x prime. So these are two families. Let's say two Q-Gronston families. Of Q Fano variety. Such that the first thing is that if we take the puncture disk, then the two family, when you restrict on the puncture disk, they are isomorphic. So my second condition is I assume that the X0 and the X0 prime, these two fibers are K-semistable. So now I have two different feelings. These two can really be just different. I mean, it really happens that there could be two different K-semistable points specialized to the same K-polystable point. As we kind of saw this morning in Janosch's talk. So now we just assume that two K-semistable. Then we conclude that the X0 and the X0 prime specialize to the unique K-polystable Fano. So again, let's just predict that inside this S equivalence, there is only one polystable point. I mean, of course, this is a standard consequence if you are having a GIT problem. But as I said, we don't have this. We don't have a GIT problem here. So we have to find some new way to conquer this. But this is the statement of the theorem. So now I can erase this conjecture because now I will basically concentrate on the separateness part. Somehow I want to discuss a little bit about the proof. I mean, I'm not going to give you every detail, but I want to give you some flavor of this kind of argument. So especially how this kind of recent new definitions help us to understand this kind of question. So let me just say proof. So let's say if I have a section in H0 minus MKX0. So this is a section which is on one family, but only on the central fiber. So now I want to define a filtration F. I want to define a decreasing filtration F on H0 minus MKX0. So basically, that the S is inside F, let's say inside the FT, FR is inside the FR H0 minus MKX0 if and only if there exists an extension S tilde. So now S tilde is inside this family of H0 minus MX over C. So I can think about C as a affine curve. So instead of the F lower star, I just write it as a global section, such that the vanishing order, the order of the S tilde. But now I look at the order of this section, the vanishing order of this section along the X0 prime, which is given by another family. So now I want to say if this is larger than R, then I say that the S is inside the FR of this section. So basically, you can think about the degree of S is given by I consider all the possible extension of S, and I look at the maximum vanishing order among all the possible extension. So that one should give you the right degree. So I mean, why I introduce this kind of thing? Because the next lemma, which is indeed not hard to prove, is that now if I take the gradient ring of this, and now I put all the m together. So now I take the gradient related to the filtration I just defined. And now I take all the gradient. This is actually isomorphic to the m prime. But now I take the gradient of r prime of h0 minus m kx. Oh, sorry, this is kx0. This is k0 prime. This is k, and here, sorry, this is define all the r prime. So this isomorphic among the gradient ring sends m r piece to m r prime piece. But what's r prime? R prime is just given by m a plus a prime minus r. So this a is basically just a x x0 prime, and similarly this a there prime is the log discrepancy of the two dividers. So basically, I look at the divisor, I look at the log discrepancy of this guy. Then I do the same thing for another family. Then this is a and a prime. And because my definition that all the families are a family of Q Fano variety, we know these two numbers are all positive. So I have this isomorphic. So essentially, what I aim to prove is that this gradient ring is kind of this kind of K-polystable object, which it is specialized to. So, but you immediately say, there's a problem if I want to I aim to do that. Because so far, I didn't use the K-semistability condition yet. So, but what's the problem here? The problem is I have this kind of gradient ring, but I don't know it's finite generated. So as I said, if you want to take the approach, in this morning we already say, if you take approach of some ring, you'd better have the ring to be finite generated. Otherwise, I mean, it's not something like people live in the first stage of evolution stage works on. So somehow we really want this ring to be finite generated. But then that somehow to be like very much like a bidirectional geometry problem, which we always aim to prove. So how do we try to show this ring is finite generated? And how the K-semistability condition built into this picture? So now, basically, we can define the beta of f. Remember, before I defined beta for, okay, sorry, I already erased it, for divisor. But actually, you can just think about divisor, the push forward of higher and higher power divisor as some kind of value filtration. And here, then, I just define the beta for filtration. I just define this to be the A times the minus kx power to n minus the volume of beta t, let's say beta t dt. So what's beta t here? So, sorry, not beta t, I'm sorry, volume t. I want to say this, volume of ft. So what's the volume of ft here? Basically, this is just the limit of m goes to infinity, that the h0, sorry, the dimension of ftm h0 minus mk x0 divided by the standard thing. So somehow I have this t, and then I have this increasing filtration. And now I look at how many sections lives in this filtration, and then I divide by m power 2n, n factorial. then this is the volume ft. Then you can prove again this is a continuous function except one point, and then I define this beta f. And this isomorphic indeed imply that the beta f plus beta prime f, you can define beta f prime. You can define the same thing for another one, for the other family. Then their sum of this is 0. So now you somehow say this interesting part, because we want our we assume our two families are all K-semistable. So every beta should be non-negative. But now we have two beta such that their sum is 0. Then this immediately implies beta f is equal to beta f prime. Sorry, beta f prime is equal to 0. Then somehow you want to use this condition as a condition to prove the finite generation. And in general, again, it's still a very challenging question. Because if that's true, then in general, you can show that somehow the K-stability is equal to the uniform K-stability, but that's not no. Here we actually strongly use the fact that this f actually comes from a divisor in a different family. So somehow this f is not itself is not a divisorial valuation over x0. So this is x0. But it somehow comes from a divisor over a family of which x0 is a central fiber. We use that property. So maybe maybe I'll just give you an explanation of some like a baby version of this result. So now let me just say prove basically a baby version. So this was inside the work with Qili and Xiaowei Wang, and also part inside the work in Blum. So basically we want to show that the theorem, I want to show that if x is K-semistable and D is satisfied that the beta D is equal to 0. So here, again, it's very important. I assume this is a divisorial valuation. For instance, I couldn't prove this theorem if I replace this divisorial valuation by general valuation. But now I just want to say that the H0 minus mkx minus nd for all the m and all the n, this ring is finite generated. Then you immediately say that the gradient ring is kind of like this, but it's a quotient. But here again, here we really use a divisor, but that one we use some like more complicated filtration. So that's why I call this a baby version of that. So now, how do we think about this sort of question? How do I prove this? This is finite generated. So I want to use this kind of construction by Qili. So basically, Qili say to study a Fano variety, we look at instead of the Fano variety itself, we look at the cone over that. So we study the cone given by x minus kx. So basically, I have the cone here. I have the Fano variety here, and then I have a cone here. So at the beginning, you might think this is kind of an ad hoc construction, because somehow, given a variety, why I construct a cone and study the cone. But if you think about it a bit more, you find that somehow what we want to do is, unlike the traditional minimal program, here we really are going to do something, change the anti-canonical ring. So somehow, now if we want to change the anti-canonical ring, we better directly work on this anti-canonical ring. And to work on this anti-canonical ring, especially equivalently, essentially just equivalent to work on this vertex point. So that's why somehow we want to take this viewpoint of working on the Fano variety itself by just working on this vertex point. And then I just do some like a stupid construction. I just blow up this point. Then I have this x. Then I call this one to be x infinity. So this is the exception divider of this block. And then I have a D here. I have a divider here. I mean, usually it could be exception divider, but let me just assume it on this. Then I can pull back this divider onto this cylinder. And now I have another divider, which I call V1. So this is, I call it a V0. So then for any PQ, let's say inside N2, which are, let's say, are co-prime, you can define the toroidal blow-up VPQ. Basically, since now I have a intersection of two divider, of course I can just like think about them as the coordinates and a generic point. Then I just take the PQ blow-up here. So that's a weighted blow-up. But why I have to choose PQ in integral number? Indeed, I can choose T, N T, which is inside 1, 0, 1, such that the VT is just the monomial, is the quasi-monomial valuation of 1 minus T along the two coordinates. So in other words, this guy is just the P plus Q time of P over P plus Q and Q over P plus Q. So somehow I basically want to rescaling this inside of 1. So particularly, if I choose En to be way to be let's say to be the blob of Vn1, then this is basically just equivalent to 1 plus n V1 over n maybe 1 plus over 1 in my second notation. So what I want to say here is that I want to show this ring to be finally generated. I have this divider over this point. If I can show that the push forward of the gradient ring of this divider is finally generated, that will imply this ring is finally generated, because it's essentially the same ring, but you change the grading a little bit. So it's, in other words, it suffices to show that if I take this pi lower stuff m E n, this kind of thing is finally generated for any n. So if you prove for one n is finally generated, then you are done. You are proof for all other. So again, this now looks very much like a bilateral geometry problem. So if you have read for instance, the BCHM paper, you know that this somehow you want to prove this kind of thing is true. You just try to prove that you can extract this divider alone. So if you have a model, if we have a model W mapped to C, such that the point here, the vertex point here, the only the only preimage of the vertex point is this divider. Then actually I just got this ring is finally generated. Then there comes this question. I mean, in general, if I have a divider over some singular point, whether it can be extracted alone, that's kind of actually quite a subtle question. And what BCHM tells you So what BCHM tells you, if we can find ideal IN and the number Cn, and the number Cn larger than 0, this is the ideal IN, such that the cone with Cn times In, this is log canonic, and the log discrepancy of this divider is less than 1. I mean, since log canonic is of course non-negative, then we can get such Wn. So in other words, the aim is now we want to find the right Cn and In here. So what's a typical candidate of this In? So now I have this En. I want to extract this In. So what in some sense, the only reasonable candidate is the In is given by, if I just consider the pi lower star minus En. So this is kind of like the only reasonable candidate. But somehow I want to do a asymptotic version. So maybe I just put an M here. Then I just write everything, put a asymptotic version here. So this is the only candidate. And now the Cn is the only candidate of this condition to be true. Is I just choose it to be the log canonic threshold of the x of the and the In. Sorry, this is the C. So this is the only candidate of the number. So now I have two natural candidates for the first row. So I only need to check the second row. But this is actually the tricky part. Somehow, why this log discrepancy of this divider with respect to this function is less than 1? I mean, that's kind of like tell you, if I push forward the divider on the base, the divider which calculates the log threshold should be just this divider itself. I mean, it doesn't always happen. So if it happens, that means you are pretty lucky. But it doesn't always happen. And here we don't claim it's happened, but we have some like other way to deal with this. So basically, I want to use something which I didn't define, but let me just say, the Chili, he defined the normalized volume function. This is kind of the function which conjecturally should give you a local stability theory, which I mean, some parts are still conjecture, but I don't have time to talk about it. But anyway, the information we want is that Chili actually made the calculation that if I take the normalized volume of all the valuation Vt I defined here. Remember, t is from 0 to 1, so I have a kind of interval of valuation. Then I take this derivative over dt. So what come out is precisely the beta invariant up to some constant. So somehow this beta invariant show up as the derivative of this volume function. So then we know this guy is 0 by our assumption, because our assumption is beta is 0. So this just tells this condition plus the condition that we know that if I look at all the infimum of the volume function of all the valuation, if you look at all the possible valuation, in this case, because I assume x is K-semistable, this is just the same as the normalized volume of the divider. This is proved by Chili. And we know this is the same as the infimum of all the ideal, or the multiplicity of ideal center on the point times the log canonic threshold power to n. This is a formula proved by Yu Chen Liu. So if we put these two together, that tells you if I look at the log discrepancy of that pair of Cni dot, this is indeed 0 plus a function of O of smaller o of 1 over n. So basically, if I have a Taylor expansion, the Taylor expansion tells you the log discrepancy here is actually something like at least the grows are like a second order of 1 over n. So particularly, it could be, let's say, maybe, sorry, maybe capital over. So it's the first order of 1 over n. But anyway, if n is sufficiently large, this basically just is sufficiently small. So here we use that the derivative of here, this is 0. So then we know that this log discrepancy could be arbitrarily small. So particularly, if I choose n to be very large, then I know this condition I want is okay. And then this way, all the way we show this is finite generated. And in general, we show that the gradient ring is finite generated. So then we can prove that this is the K-semistable object, which then has a uniform K-polystable, which has a unique K-polystable object. So that's the title of my talk. So I still have like 1 minute. Let me just say, now if we are less ambitious, we are just want to look at the open locus, which is parameterized by uniform K-stable Fano varieties. So this is conjecturally the same as K-stable, but it's not necessarily, well, so far we don't know. But in general, it's not necessarily proper anymore because I really saw some object. And then this result tells you it's basically a Deleuze stack. And for that kind of the stack, the Zariski openness is indeed known by the work of Blum and Liu. So particularly, if I just look at the uniform K-stable, then it's parameterized by a separated Deleuze stack. So particularly, we know this guy has like a cosmology space. And then the question is whether you can show the cosmology space is projective or not. This is not completely known, but recently, Kodogoni and Patakfavi has major progress along this line. Okay, let me stop here. Thank you. Yeah, I mean, I don't know. Well, there is some intuition come from the family that you have this test configuration family. Then somehow in this BHJS work, they somehow kind of relate the C star action, the weight action, as a certain valuation, which I defined, the vanishing order. So that's, you can think about it as compare the family and with the trivial family. So, but somehow to generalize that to this kind of like a non-trivial, like a more relative family. I mean, yeah, we basically that plays some like intuition.